All right, welcome to our next video about vector equations. So a really common kind of problem in linear algebra is to ask a question where if you're given some vector like w, 5, 0 is out here, and you want to write that as a linear combination of u and v. So hopefully you understood linear combinations from the 3 blue 1 brown videos and also from the online textbook reading. But the basic idea is we want to know how can we do some kind of scalar multiple of v, which means multiplying the coordinates 2 and 1 by something, which has the effect graphically of getting you some other point on the line through the origin and the point 2, 1. So for example, 2v would be out here. You just get a longer version of that. Like so. And we want to do something times v like that, and then add that to something times u. So we could also do any scalar multiple of u, which would give you something sort of like that. So you could say, for example, take u down to about, I don't know, somewhere around here it looks like, and do, I don't know exactly how much I want to scale u by. So let's say that this is some vector x1 times u. So I don't know what that scalar x1 is. And then from there, I could do something times v and add that to that result. And I don't know exactly how far I need to go here, so let's just call that x2 times. And just to reiterate, the goal is to find x1 and x2 that makes this vector equation true. And based on the picture, I can make a, I don't know, a halfway decent guess at what x1 should be. Like, it looks like to get to this point, I'm not going quite as far as 2u. 2 times u would be twice as long, which is here. So it looks like maybe this is about 1.8 times u. And we want to do that plus something times v. This looks like this vector here is longer than v. Maybe not quite as long as 2v. So let's call it 1.8v. And let's see what that comes out to be. Do we get w? Well, 1.8u means multiply each of these coordinates by 1.8. Doing 1.8v gives you 3.4, 1.8. And if you add these up, what you'll get is 5.2 and 0. So it's sort of close. It's not 5.0, but it's 5.20. And of course, we want a way to get this exact, rather than just like trying to eyeball it from pictures all the time, which isn't a very good engineering practice. So how do we get it exact? We're going to solve this equation. So to write this equation out, I'm just going to rewrite u again, but I'll rewrite u as the one negative one there, plus x2 times 2, 1, which looks like this. So this is what we call a vector equation. Which is an important thing to know, that whenever we have an equation that has a vector on one side, usually written as a linear combination result of some vectors, and then a vector on the other side, that's what we mean by vector equation. So anyways, what we can then write this in a different format, because the definition of x1 times this just means we're going to multiply each of these entries in this vector by x1. So 1 times x1 is x1, negative 1 times x1, negative x1, so we're doing that, plus this vector here, x2 times 2, 1 is defined to be 2 times x2 and 1 times x2. And that needs to equal the vector 5, 0. also the sum of these two vectors is defined to be just the vector that you get when you add up these two components to get the new first component, and then add up the two y components to get the new y component. And again, that vector needs to equal 5, 0. And let's think, what does it mean for two vectors to be equal? Like, for example, this vector here is not exactly equal to w because the 5.2 is not exactly equal to 5. The 0 is equal to 0, but in order for two vectors to be equal, you need to have all of the components to be equal, not just one of them. So saying that these two vectors are equal is the same as saying that this component is equal to 5 and this component is equal to 0. And we can write that as this system of two linear equations here. And once we see that we're really just talking about a system of linear equations, we can solve that the normal way by writing it as a matrix. And then row reducing it. In this case, it's pretty easy to row reduce it. We can just add a copy of row 1 to row 2 to replace row 2. And this is what you get. We can then do a scaling operation on, this is my little symbol that means these matrices are all row equivalent to each other. So we're going to do a scaling operation here. We're going to get 0, 1, and then 5/3. We can just do -2 times this row plus the second row to clear away, sorry, plus the first row to clear away this 2 in the first row. So that's going to leave you with a 1, a 2 minus 2 times 1 gives you a 0, and then 5 minus 2 times 5/3 is 15/3 minus 10/3 is also 5/3. So when you rewrite this as a system of equations, it gives you that x1 is equal to 5/3, also known as 1.6 repeating, and x2 is also equal to 5/3. And that tells you exactly what you need to do. And you could check that if you want. If you do 5/3 times 1 -1 plus 5/3 times 2 1, hopefully it does give you exactly 5 0. So we weren't too far off with a 1.8, but it's not as close as you usually want to get. So the moral of the story here, and this is what's really important, this is a crucial idea in linear algebra, is that a vector equation saying like these are coefficients of some vectors that we want to add up to get some other vector is the same as writing this system of equations that has the coefficients of x1 are the first vector, the coefficients of x2 are the other vector, and the numbers on the other side is the vector result you're trying to get. Okay, so here is what I just said, kind of written out in more general. So when you have a vector equation with some linear combination of some vectors on the left, and you want to get some result vector on the right, and the v vectors and the b vectors are all given, and you don't know what the weights are, what the coefficients x1 through xp that you're trying to get are. The solution set is the values of those unknown variables that makes it work. That's what we mean by a solution, is the x's. So that system has the same solution set as the linear system with this augmented matrix. So here's the augmented matrix part written out over here. Here it is written as a vector equation. Here's the system of equations in the middle. So there's these basically, these three things we're talking about. A system, its augmented matrix, and the the vector equation you started with. So here's a little exercise for you to translate between those three different ways of writing things. Here's a system of equations. Write it as a vector equation. And for number 2, here is a vector equation. Write that as a system of equations or and also as an augmented matrix. Should be pretty quick just to check that you got that. If you're having trouble with these exercises, definitely ask for help in class and we can go over it then.